Diving deep. Artificial intelligence and deep learning. Artificial intelligence, or AI, is transforming our world. From self-driving cars to personalized medicine, AI is changing how we live and work. Deep learning is a powerful type of AI. It uses artificial neural networks, inspired by the human brain, to learn from data. Imagine a vast network of interconnected nodes, each processing information. These networks can analyze massive amounts of data, identify patterns, and make predictions. They power everything from image recognition to language translation. The more data they process, the more accurate they become. But training these complex neural networks requires immense computational power. This is where the role of specialized hardware becomes crucial. Just like a powerful telescope helps us see deeper into space, powerful hardware allows us to explore the depths of deep learning. Training titans. The need for powerful hardware. Training a deep learning model is like teaching a child to ride a bike. It takes time, patience, and lots of practice. In this case, the practice involves feeding the model massive datasets and adjusting its parameters until it can make accurate predictions. This process demands incredible computing power. Imagine processing millions of images or translating thousands of pages of text. Ordinary computers would struggle with such intense workloads. This is where graphics processing units, or GPUs, come into play. GPUs were initially designed for rendering graphics in video games, but their unique architecture makes them ideal for deep learning. To understand why, we need to first look at traditional CPUs. CPUs, the all-rounders. Central processing units, or CPUs, are the brains of our computers. They excel at handling a variety of tasks quickly and efficiently. Think of a CPU as a multi-talented chef who can cook several dishes simultaneously, switching between tasks seamlessly. CPUs are designed for general-purpose computing. They have a few powerful cores that handle complex instructions one after another. This makes them great for tasks like running operating systems, browsing the internet, or editing documents. However, deep learning requires a different approach. Training neural networks involves performing massive numbers of simple calculations simultaneously. This is where GPUs shine. Section 4. GPUs. The deep learning specialists. GPUs, unlike CPUs, are designed for parallel processing. Imagine a large team of cooks, each specializing in a specific task. They work together, each handling a small part of the recipe, to prepare a banquet much faster than one chef could alone. GPUs have thousands of smaller cores that can perform simple calculations simultaneously. This parallel processing power is ideal for the matrix multiplications and other operations that underpin deep learning. Furthermore, GPUs boast significantly higher memory bandwidth than CPUs. This means they can access and process data much faster, which is crucial when dealing with massive datasets. Finally, GPUs excel at floating-point arithmetic, the type of math used extensively in deep learning. Section 5. Why GPUs reign supreme: speed and scale. The advantages of GPUs translate to significantly faster training times for deep learning models. What might take days on a CPU can be accomplished in hours or even minutes on a powerful GPU. This speed advantage is crucial for researchers and developers who need to iterate quickly and experiment with different models. Moreover, GPUs offer superior scalability. Multiple GPUs can be interconnected to form powerful clusters, enabling the training of even larger and more complex models. In the world of deep learning, where time is of the essence and model complexity continues to grow, GPUs have emerged as the undisputed champions. They provide the raw computational power needed to unlock the full potential of AI. Now that you understand why GPUs are essential for deep learning, get ready to dive into some code in the next section. We'll explore how to harness the power of GPUs to train your own deep learning models.
In this video, we will learn on CUDA GPU, how to target single GPU instance and multiple GPU, how things goes in hand in training a large language model.
Let's get started how things goes on with GPU. We are going to use Google Colab, which already provides T4 GPU in runtime. Before kicking things off, let me clear we will work with text how things goes with large language models, how PyTorch get into help in later section in code from scratch. Stay tuned for that. We are currently just building the concept and setting up the bricks before building the house. Let's get coding. Import torch. print torch dot underscore underscore version underscore underscore. NVIDIA Semi. There will be a tab like this, which show that you are running your model on GPU, not CPU. Let's break down the basic differences between a GPU graphics processing unit and a CPU central processing unit. Purpose. CPU designed for general purpose processing. It handles a wide variety of tasks, including running operating systems and applications. It's good at executing complex instructions and performing sequential processing. GPU optimized for parallel processing and is specifically designed for rendering graphics and handling tasks that require massive amounts of data to be processed simultaneously. GPUs are great at handling repetitive tasks and parallel computations. Architecture. CPU typically has a few powerful cores, usually between 2 to 16, that are designed to handle complex instructions and run multiple processes. It excels at single-threaded performance and tasks that require fast, sequential processing. GPU contains hundreds or thousands of smaller, simpler cores designed to perform many operations simultaneously. This makes it ideal for tasks like rendering images, video processing, and running parallel algorithms. Performance. CPU provides higher single-threaded performance and is better suited for tasks that require high-speed computations and complex decision-making. GPU offers high parallel processing power, which makes it faster at tasks that can be divided into many smaller, simultaneous operations, such as graphics rendering and machine learning tasks.
If you have stayed tuned in the earlier video, the CUDA availability on RunNMG cell had come false. But this time it will show up true as we have triggered the GPU. Print torch.CUDA is underscore available. Tensor underscore 1 torch.tensor 1, 2, 3. Tensor underscore 2 torch.tensor 4, 5, 6. Print tensor underscore 1 tensor underscore 2. Tensor underscore 1 tensor underscore 1 dot to CUDA. Tensor underscore 2 tensor underscore 2 dot to CUDA. Print tensor underscore 1 tensor underscore 2. Single runtime GPU. X underscore train torch dot tensor. -1.2, 3.1. -0.9, 2.9. -0.5, 2.6. 2.3, -1.1. 2.7, -1.5. Y underscore train torch dot tensor 0, 0, 1, 1. X underscore test torch dot tensor. -0.8, 2.8. 2.6, -1.6. Y underscore test torch dot tensor 0, 1. From torch.utils.data import dataset. Class toy dataset dataset. Def underscore underscore init underscore underscore self xy with self dot features x. Self dot labels y. Def underscore underscore getim underscore underscore self index. 1 underscore x self dot features index. 1 underscore y self dot labels index. Return 1 underscore x, 1 underscore y. Def underscore underscore len underscore underscore self. Return self dot labels dot shape 0. Train underscore ds toy dataset x underscore train y underscore train. Test underscore ds toy dataset x underscore test y underscore test. From torch.utils.data import data loader. Torch.manual underscore seed 123. Train underscore loader data loader. Dataset train underscore ds. Batch underscore size 2. Shuffle true. Num underscore workers 1. Drop underscore last true. Test underscore loader data loader. Dataset test underscore ds. Batch underscore size 2. Shuffle false. Num underscore workers 1. Class neural network torch.nn.module. Def underscore underscore init underscore underscore self. Num underscore inputs. Num underscore outputs. Super dot underscore underscore init underscore underscore. Self dot layers torch.nn dot sequential. First hidden layer. Torch.nn dot linear num underscore inputs 30. Torch.nn dot relu. Second hidden layer. Torch torch.nn.linear3020, torch.nn.relu, output layer, torch.nn.linear20, num_outputs, def forward self x, logits self.layers x, return logits. Import torch.nn.functional as f, torch.manual_seed 123. Model neural network num_inputs 2, num_outputs 2. Device torch.device CUDA if torch.CUDA is underscore available else CPU new. Model to device new. Optimizer torch.optim.sgd model.parameters LR0.5. num_epochs 3. For epoch and range num_epochs. Model.train. For batch_IDX features, labels and enumerate train_loader. Features, labels features.to device, labels.to-device new. Logits model features. Loss f.cross_entropy logits, labels loss function. Optimizer.0_grad. Loss.backward. Optimizer.step. Logging. Print f epoch 103d num_epochs 03d. F batch IDX 03d len train _loader 03d. F train val loss :2f. Model.eval. Optional model evaluation. Def compute _accuracy model, data loader device. Model.eval. Correct 0.0. Total _examples 0. For IDX, features, labels and enumerate data loader. Features, labels features.to device, labels.to device new. With torch.no_grad. Logits model features. Predictions torch.argmax logits, dim1. Compare labels predictions. Correct torch.sum compare. Total _examples len compare. Return correct total _examples.item. Compute _accuracy model, train _loader, device. Compute _accuracy model, test _loader, device. Multiple GPU. For targeting multiple GPU, you can use this script. Remember, Colab is just for experimenting. Feel free to experiment on your own. We'll be putting more links in description checkout and give it a try. Import torch. Import torch.nn.functional as f. From torch.utils.data import dataset, data loader. New imports. Import OS. Import torch.multiprocessing as MP. From torch.utils.data.distributed import distributed sampler. From torch.nn.parallel import distributed data parallel as DDP. From torch.distributed import init _process _group destroy _process _group. New function to initialize a distributed process group 1 process GPU. This allows communication among processes. Def DDP _setup rank world _size. Rank of machine running rank 0 process. Here we assume all GPUs are on the same machine. os.environmaster _addr localhost. Any free port on the machine. os.environmaster _port 12345. Initialize process group. Windows users may have to use glue instead of NCCL as backend. NCCL NVIDI a collective communication library. Init _process _group backend NCCL rank world _size world _size. Torch.CUDA.set _device rank. Class toy dataset. Def _init _self xycat. Self.features x. Self.labels y. Def _getim _self index. 1 x self.features index. 1 e self.labels index. Return 1 x, 1 y. Def _len _self. Return self.labels.shape0. Class neural network torch.nn.module. Def __init_self num_inputs num_outputs super.__init__ self.layers torch.nn.sequential. First hidden layer. Torch.nn.linear num_inputs 30. Torch.nn.relu. Second hidden layer. Torch.nn.linear 30 20. Torch.nn.relu. Output layer. Torch.nn.linear 20 num_outputs. Def forward self x. Logits self.layers x. Return logits. Def prepare _dataset. X _train torch.tensor. -1.2, 3.1. -0.9, 2.9. -0.5, 2.6. 2.3, -1.1. 2.7, -1.5. Y_train torch.tensor 0, 0, 1, 1. X _test torch.tensor. -0.8, 2.8. 2.6, -1.6. Y_test torch.tensor 0, 1. Train _ds toy dataset x _train y_train. Test _ds toy dataset x _test y_test. Train _loader data loader. Dataset train _ds. Batch _size 2. Shuffle false. New false because of distributed sampler below. Pin _memory true. Drop _last true. New chunk batches across GPU is without overlapping samples. Sampler distributed sampler train _ds new. Test _loader data loader. Dataset test _ds. Batch _size 2. Shuffle false. Return train _loader test _loader. New wrapper. Def main rank world _size num _epochs. DDP _setup rank world _size new initialize process groups. Train _loader test _loader prepare _dataset. Model neural network num _inputs 2 num _outputs 2. Model dot to rank. Optimizer torch.optim.sgd model.parameters LR0.5. Model DDP model device _IDs rank new wrap model with DDP. The core model is now accessible as model.module. For epoch in range num _epochs. Model.train. For features, labels in train _loader. Features, labels features dot to rank, labels dot to rank new use rank. Logits model features. Loss f dot cross _entropy logits, labels loss function. Optimizer dot 0 _grad, loss dot backward. Optimizer dot step. Logging. Print fgpu rank epoch 103d num _epochs 03d. F batch size labels dot shape 0 03d. F train val loss dot 2f. Model dot eval. Train _acc compute _accuracy model train _loader device rank. Print fgpu rank training accuracy train _acc. Test _acc compute _accuracy model test _loader device rank. Print fgpu rank test accuracy test _acc. Destroy process group new cleanly exit distributed mode. Def compute _accuracy model data loader device. Model.eval. Correct 0.0. Total _examples 0. For IDX features, labels and enumerate data loader. Features, labels features dot to device, labels dot to device. With torch.no _grad. Logits model features. Predictions torch.argmax logits, dim1. Compare labels predictions. Correct torch.sum compare. Total underscore examples len compare. Return correct total underscore examples.item. If underscore underscore name underscore 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 main underscore underscore print PyTorch version torch dot underscore underscore version underscore 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 print CUDA available torch dot CUDA dot is underscore available. Print number of GPUs available torch dot CUDA dot device underscore count torch dot manual underscore seed 123. New spawn new processes. Note that spawn will automatically pass the rank. Num underscore epochs 3. World underscore size torch dot CUDA dot device underscore count. mp dot spawn main args world underscore size num underscore epochs nprox world underscore size. nprox world underscore size spawns one process per GPU. So that's it for today. Remember, the best way to learn is by doing so. Keep up the good work, and happy coding. Stay curious. We'll see you in the next video. Thanks for watching.